Assalamu alaikum. Now we continue with solar thermal applications part 2. We will be focusing mostly on the concentrating solar energy technologies. The solar concentrator or concentrated solar power, whatever way you want to name it, they are categorized based on the required temperature. So when we are using for low temperature applications, we really do not want to go for the concentrating techniques because they're expensive. It will mostly start from medium temperature to high temperature, and the medium temperature range is somewhere between like 60 to 260 to 250 degrees Celsius, like that. And the high temperature can reach up to like 700, 800, up to 2000 degrees Celsius. Okay, what is concentrated solar power or solar concentration, solar energy concentration? Basically, we use kind of lens or reflectors. They are converging into same point. So that means it's converting the solar radiation into high temperature heat, right? You have all experienced when you have used a lens and you held it under the sun. It can create so high temperature that it can start burning things, right? So the exact same thing is applied here, either through lens or sometimes through reflectors. So we are going to learn about different types of reflectors available in the market, and like what can we do with this high temperature also we are going to learn about it. So why do we need concentrating solar power? It is because the higher the temperature is, right? So if you have gone through the Carnot cycle, Carnot power cycle, you should remember that the higher temperature will always increase the cycle's efficiency. And if we can, like as I have mentioned, high temperature can be up to 2000 degrees Celsius. So it is quite high temperature for generating power or any other application. Mostly for running the vapor power cycle, we can use it. And then this one can be captured, this high energy can be captured through energy storage also. And we can actually provide electricity either from the power cycle, or maybe in some cases we concentrate the light on the photovoltaic to generate the electricity. Now we will talk about the most commonly available or most matured technology, which is called the parabolic trough collector, PTC. So as you can see the design, the parabolic term comes from the shape of the inner surface of the absorber, and based on the base design it can be flat, it can be like bifacial, right? It can be wedged shape, or it can be tube absorber at the center. So the thing is, it captures the sunlight. So say for example one radiation is coming in, then it will capture it inside. It is reflected, but reflected to the other wall, then reflected to the center. Okay, so you can see that all the things falling on it is it's not possible for it to readily get reflected and go out. So it's like a kind of trap for the solar irradiation incoming. And we can design it in another way, like you can see that for actual application we make the thing parabolic, the thing curvature reflector, then the sunlight falls on it, and then you can see it's reflected to the central pipe, and that is called the absorber tube. So this absorber tube will carry the heat transfer fluid pumped through, and it will be always be getting heated from the reflected sunlight, and the temperature can reach up to 400 degrees Celsius, which is very high temperature, good enough to run a vapor power cycle. This illustration is to show you how the solar irradiation is coming in and then getting reflected in the parabolic surface. And if you can design your absorber accordingly, it will receive all the sunlight falling. So like from this direction, they are also concentrating on this. So it's a good source of heat, right? The surface is reflecting all the sunlight. So depending on the shape, like they can be called as an involute reflector also. And on the top there may be a glass cover if you want to make it like I mean the thing all combined together. So adding up the glass cover increases the greenhouse effect inside, aiding in the increase in temperature of the working fluid or heat transfer fluid inside the absorber. Now some detailed description about parabolic trough collector or PTC. So as we can see, it's a special type of concentrator that has a parabolic cross section, right? Okay, mostly like circular parabolic, but it's linear in the third dimension. So that means the parabolic shape is extended linearly to make a long reflector. Now the shape of this reflector, it causes the sunlight to be concentrated along a line at the focus. It's not a point base, rather it's a line at the focus of the parabola and the line that runs along the length of the trough. So we have to place our absorber tube along that particular line where the sunlight is getting concentrated. A heat receiver, which is mostly called the absorber, is positioned exactly at this focus, right? And also the heat transfer fluid is pumped through the pipe and carries the heat away. Its temperature range may not be that extremely high like the other one we're going to see later, the tracking based concentrators, but this one is fairly enough up to 400 degrees Celsius. And we can understand that although it's not directly relevant to the tracking, but it would be at least some degree of tracking should be there to capture the sun from morning and the afternoon. In this diagram, we will see how the PTC works for power generation. I believe you can remember the vapor power cycle, right? The Rankine cycle where we used to have a boiler and the boiler would be sending the superheated steam to the turbine. The turbine will be generating electricity or whatever form of work that is required. Then the rest of the exhaust steam will be coming to the condenser to get condensed. Then it will be pumped back to the boiler pressure again. So if you see, if we are actually doing the thing over the boiler here, right? If we are focusing on the boiler, we can actually, instead of supplying fuel, burning fuel, generating heat and boiling water, instead of doing that, we can attach this thing to a PTC, right? So if the temperature can go up to like 400 degrees Celsius, it can be fed to the boiler and then it can be running the power cycle. So this one in general is called the concentrated solar power. Okay, when we are generating power by concentrating the sunlight. This is the real life example of how we are getting what is going to be parabolic collector. So we have seen that previously the parabolic concentrator, right? We didn't really have to do the tracking of the sun. But if you really want a very precise one, and you want to capture all the sunlight throughout the day, you should incorporate sun tracking collectors. So this energy delivery temperature can be increased, and if you can decrease the area from which the heat losses occur. So temperatures far above those attainable by the flat plate collectors can be reached if a large amount of solar irradiation is concentrated. And how can we do that in a small collection area? When we are adding up an optical device between the source of radiation and the energy absorbing surface. So that means the energy absorbing surface will always be pointing toward the source of radiation, that is the sun. Now we start with the sun tracking concentrator collectors, and I'm going to talk about the Fresnel lens concentrator at the beginning. The concept is very much like the lens we all know, like we can concentrate the sunlight with a small lens, and then we can, if we want, we can set the fire also because the temperature will be so high, right? So this Fresnel lens is differing from the conventional glass lens in a term that it follows a special method of focusing the sunlight. If you see on the right here, this one is a This one is the top view of the Fresnel lens. So you can see there are many circular notches, right? Okay. So each of these circular notches, they will be focusing the sunlight. So this series of concentric grooves or rings that will bring the light toward a central focal point, which is here. So what advantage does Fresnel lens has over other like heavy glass based lens? Uh, what we have here is, since we are making many rings, it gives us uh, multiple focal distances, right? Like compared to this, so all are designed to be focused at the same point, but through the multiple sources. If you have to make it by a very big convex lens, it will be quite heavy and quite big, right? Also, we can use any type of transparent polymer like PMMA to make this lens, and it mimics a curved lens, but it uses less material and is much thinner. Plus the focal point is also like, for all the rings is a one single focal point. So we can capture the lights all together within a very thin thickness, very small thickness of the lens. Now we can see that how we are using this Fresnel lens concentrator. So this is the tracker used, so it will be moving along with the sun's path. You can see some of the shadows of these circular grooves, and the sun will come in. You can see it's getting concentrated here, right? The temperature can go up high, quite high, that you may use molten salt as the heat receiver fluid. So you can see there's a sample of how we can use Fresnel lens for cooking. Okay, so you have to hold the Fresnel lens here, and then it will be coming back to your stove as a stove, and then either you want to boil the mineral oil circulation system by hot oil system, you can get the heat, or like any other type of molten salt or anything, you can capture the heat, then you can use that heat as your in the cooking unit. Okay. Another type of concentrator based on the tracking is linear Fresnel reflector. It doesn't have anything to do with the Fresnel lens, okay? But still the name Fresnel is there because they are kind of imitating the focusing behavior of a Fresnel lens using segmented linear mirrors. So you can see in the diagram here, these are all the linear Fresnel mirrors. And you can see the sunlight, they are falling on that, and then they are concentrating along a single line, right? So there are many segments, and all these segments are concentrating toward a single line. So that it mimics the Fresnel lens behavior. Fresnel lens has many concentric rings, right, or the grooves. So this is called the linear Fresnel reflector, and each mirror tracks the sun along a single axis. Okay, the mirrors reflect sunlight toward the fixed linear receiver mounted on the structure above the mirror, somewhat like that parabolic trough collector that we have previously seen. And we usually use water, thermal oil, or molten salt as a heat transfer fluid. This thing is used to produce either steam for turbines or industrial process heats. Now we are going to have a look at a higher capacity concentrator, which is called the heliostat system. And the heliostat system focuses light onto the central tower receiver. It's like a tower. So you can understand the reflected length. I mean, the focal length is quite long, but it also produces very high temperature, 500 to 1000 degrees Celsius. And since it's up to 1000 degrees Celsius, it is safer to use heat transfer material like molten salt, okay, for high capacity power cycles. So let us have a look how this heliostat receiver and concentrator works. So you can see that there are inclined mirrors, which is called the heliostat field. Then the sunlight is falling on them and getting directed toward a single point onto the tower, and where we can supply the heat transfer material like molten salt. Okay, so this is there is a central receiver instead of a line receiver. Now, how does it differ from the linear Fresnel lens? Because linear Fresnel lens, we have also seen there are a series of mirrors and they are reflecting it along a line. Okay, we understand it's a central receiver, and for linear Fresnel lens it's along a line. So no wonder heliostat can achieve a very high temperature because all the sunlight is focused onto a single point. Now this comparison will make it more clear the difference between the heliostat and linear Fresnel reflector. So for heliostat we use flat or slightly curved, while for linear Fresnel reflector LFR we use long and flat mirrors. And heliostat has a dual axis tracker and linear Fresnel reflector has single axis. So the tracking is by dual axis, follows the sun in two directions, and single axis is in one direction. Sunlight focus for heliostat, it's on a central tower receiver on a particular point, and for linear Fresnel reflector it's onto an elevated linear receiver, right? So efficiency is higher optical efficiency for heliostat because definitely it's doing the more precise tracking, but for LFR it's lower compared to heliostat. Cost is definitely higher for the heliostat because you are maintaining this dual axis tracking, right? So that's why it's a higher cost, plus capital cost is also higher. And for linear Fresnel reflector, since we are not first of all bothering about that dual axis tracking, plus they are all very long Fresnel mirrors, just flat mirrors, so it's like lower cost and simpler design. Land use, heliostat requires larger open space, and linear Fresnel reflector requires more compact layout. And temperature wise, heliostat gives us the higher temperature, definitely high efficiency, and a linear Fresnel reflector gives us a moderate, typically 250 to 550 degrees Celsius. So we can understand that for heliostat concentrator we should be going for larger scale power generation, right? And for linear Fresnel lens it can go up to like medium scale or industry process heat, okay, or hybrid CSP, desalination, all this. Now we will have a broader comparison between Fresnel lens concentrator, PTC, and heliostat. Okay, so we can see in terms of concentration ratio, Fresnel lens is medium to high concentration from 10 times to 500 times. Parabolic TRAO is within the range of medium, 10 to 80. Solar tower is very high, 500 to 1000. Cost for Fresnel lens is low. Parabolic TRAO collector is medium, heliostat is high. Complexity for Fresnel lens is low medium, PTC is medium, heliostat is high. And typical application, if you can see, Fresnel lens concentration, solar cooker, desalination, I mean low to mid temperature ranges. Parabolic TRAO, solar thermal electricity can be generated also, plus the other application like low to medium temperature applications. And solar tower by heliostat will give you very precise, very high temperature, so you can actually use it up for utility based concentrated solar power development. Now there's a quick touch up on how we can capture this heat for the time when the sun is not in the sky, that means after the sunset or during the cloudy time, right? So we use thermal energy storage, in short it is called TES, and this can be broadly classified as two types. One is the sensible heat. The example can be molten salts, rocks, all these things. They are there during the capture of the energy and then they get heated. So later on when the sunlight is not there, they release back the heat. So they have to have a high heat capacity so that they can actually hold it for a long time. And the latent heat storage is like the thing will melt, we change it into from solid to liquid. So when something is transformed from solid to liquid, it will require a huge amount of latent heat of melting. So say for example paraffin wax. If you take paraffin wax Okay. So paraffin wax will be melting around 60 to 70 degrees Celsius just for a low temperature application, but when it's melting it is capturing the latent heat. Okay. And later on, when after the sunset, this molten paraffin wax will be releasing back its latent heat again because it will be solidifying. So latent heat storage gives us this possibility of capturing the heat due to the high amount of latent heat. We are almost toward the end. So advantages, what are the advantages of CSP? Basically, it's like renewable power can be dispatched, then large scale potential because we have high temperature, thermal storage, we can integrate the thermal storage and keep it using for longer hours. Plus, we can do the hybridization with fossil fuel. So when the fossil fuel is available, but maybe it's the daytime and we have the capability to concentrate the sunlight, we can run on the CSP mode, and after the sunset we can go back to the fossil fuel based power production mode. Now let's touch up with some of the limitations of CSP. Definitely CSP is dependent very much on the high direct normal irradiance, DNI. It is not that efficient in capturing the diffused irradiation. It does give some improvement in the zone like tropical area where the diffused solar irradiation is higher, but it is mostly dedicated for high direct normal radiance concentration, and it will require large land and water requirements. Definitely high temperature to cool it off or use it, we need the water requirement. Plus if you're setting up the heliostat system, it will require large land requirement. That some future prospects, like we can keep on working on improving the receiver and reflector materials, then we can integrate it with hydrogen production or hybrid CSP photovoltaic plants. And then it is a good news that the costs have been falling with scaling it up for future, so we can have some good power generation capability from the sun if we use CSP in future. Thank you. Assalamu alaikum.